let us now look at one more dimension of Indian mathematics, which is what is called magical squares. And Indians have been working on it from BCE. So let us start with this table here. You see two tables here. We will focus first on the table on the left. What you see on the table on the left is if you add all the rows, sum of rows will add up to a number 34. 12 plus 3 plus 6 plus 13 is 34. Similarly, if you take the third column, 6 plus 4, 10, 10 plus 9, 19, 19 plus 15, 34. You take a diagonal, 12 plus 5, 17 plus 9, 26 plus 8, 34. The other diagonal, 13 plus 4, 17, 17 plus 16, 33, 33 plus 1 is 34. So this is called a magic square, a simple magic square. A magic square is one in which all rows will add up to the same number, all columns will add up to the same number, and the two diagonals will also add up to the same number. But there is something called pan-diagonal magic square. What it means is, don't think, imagine that instead of a sheet like this, if this 4 by 4 matrix is like a torus, a cylinder, imagine it is like a cylinder, then there are more diagonals, not just the two diagonals. So in the first square, I have colored some numbers, because if you imagine it like a cylinder, then after 6, 5 and 7, next number will be 8, because if you turn it like that, 8 will come to the other side. So that is another diagonal now. If you add to that diagonal, let us see what happens. 6 plus 5 is 11, 11 plus 7 is 18, 18 plus 8 is 36. It doesn't add up to 34. Whereas if you look at the matrix 4 by 5 matrix on the right side, what will happen is row sums will be 34, column sums will be 34, all possible diagonals will also be 34. So that is called a pan-diagonal magic square. That is even more tougher. So Indians have worked on this very well, some 800 years, 2000 years back and so on. So in this module, in this video, let us try to understand some of these things that Indians have done. So the construction of such magic squares has been known to India from very early times. Indian mathematicians specialized in the construction of a special class of magic squares called Sarvatobhadra or pan-diagonal magic squares. So Bhadra Ganita is the name for the study of magic squares in the Indian mathematical tradition. So we are now talking about Bhadra Ganita actually. Various 3 by 3 magic squares. See, what I showed you is 4 by 4. The next smaller one is 3 by 3. So various 3 by 3 magic squares are attributed to the ancient astronomer Garga, who lived in 100 BCE. The work of Kakshaputa of Nagarjuna, who lived in 100 CE, describes a method for constructing 4 by 4 magic squares, which gives pan-diagonal magic squares when the magic sum is even. So this is 2100 years back. Magic squares have been used to address certain combinatorial issues. So it is not for fun, it also has application involving arithmetic. So therefore magic squares have a certain application actually. For example, Varahamihira, I just now alluded to it. Varahamihira, who in 587 CE, that is his time, made use of a 4 by 4 magic square to specify varying proportions of 4 ingredients that can be mixed to prepare different perfumes. So now you see an application. Each combination of that will add up to the final result, same sum number, like that. A 4 by 4 square occurs in a Jaina inscription of the 11th century CE, found in the ancient town of Khajuraho. And a similar square dated 1480 CE was found in the Gwalior fort. And interestingly, the first chapter of the notebooks, Srinivasan Ramanujan left 3 notebooks of his results and so on. The first chapter of the notebooks of Srinivasa Ramanujan is on magic squares. So all these show that this is also an area where Indians have been spending time thinking about it, coming with interesting solutions, even applications as Varahamihira has indicated and so on. So let us now get into it and see one or two methods. So let us start with Nagarjuna's scheme for generation of a 4x4 pan-diagonal magic square. Let us look at that first. So what you see here, there are three 4x4 matrices you see here. First one is a matrix having numbers 0, 1, 0, 8, etc. You may wonder where are these numbers coming from. They are coming from this shloka, which again uses Katapayati. In Katapayati, all vowels are 0. So as starts with 0, the first one. Ka is actually 1. Other syllables can be pure consonants are to be ignored. E is again a vowel, so it is 0. So Da is 8, Na is 0. So it goes on like that. So if you take Arka Indu Nidhanari, Tena Lagna Vinasanam, it's easy to remember that shloka. With that shloka, with Katapayati, you can actually generate this 4x4 matrix. Then he gives another formula in which he comes with this. So what is it doing? It is replacing wherever there are zeros, it is replacing with something else. Just see here. Other numbers remain. 1, 9, 8, 2, all those remain. Wherever there are zeros, there is something replaced. So now we have to use this to generate a magic square for any sum. For example, if you are interested in 100, then 100 is equal to 2n. That is what Nagarjuna's thing. So n becomes 50. So you put n here, 50 minus 3, 47. 1, nothing has to be done, so 1 remains. 50 minus 6 is 44. 8 remains. So like this, all these numbers are deduced from here from a knowledge of n. So this is now a magic square. It's a pan-diagonal magic square. You add any way, it will add up to 100. So let us just see. 47 plus 1 is 48. 48 plus 44 is 92. 92 plus 8 is 100. We will look at a diagonal. 47 plus 9 is 56. 56 plus 3 is 59. 59 plus 41 is 100. This is fine. It says pan-diagonal. So let us try this. 44 plus 9, 53. 53 plus 6 is 59. The next number is here. If you roll it as a torus, this number will come here. So this also adds up to 100. So this is a formula for magic square as you see here. The mathematics involved in the construction of magic squares and other magic figures was first systematically and elaborately discussed by mathematician Narayana Pandita, 1356 CE, in his Ganita Kaumudi. Some of his methods were unknown in the West, and actually very recently they were discovered by the efforts of several scholars. That's the situation actually. The last chapter of the seminal work Ganita Kaumudi is devoted to Bhadra Ganita, which contains 55 verses giving rules and 17 verses giving examples. All those are the pan-diagonal magic square problems, and all those are described by Narayana Pandita in 1356. Narayana presented a general method for filling up a 4x4 pan-diagonal magic square by an arithmetic sequence using a succession of Turaga Gati. Turaga is horse. So Turaga Gati means horse movements. That's how he describes. In fact, positioning one at the left top corner, he generated 24 such squares, especially if you have to fill in 1 to 16 numbers, and concluded that in all there are 384 such pan-diagonal squares. In the 20th century, it had to wait till 20th century. In the 20th century, a few mathematicians studied the 4x4 pan-diagonal magic squares and also came to the same conclusion that only 384 such pan-diagonal squares are possible. Maybe they gave a proof and all that for what Narayana Pandita said some 800 years back. So they did further work and came with some properties and so on. So let us just look at some of those properties and try to understand how to construct a 4x4 pan-diagonal magic square. We will take an example and see. So there are three properties which we should be aware. Property 1 says in a pan-diagonal 4x4 magic square, the entries of any 2x2 subsquare, if you take any 2x2 subsquare, formed by consecutive rows and columns add up to the magic number. So that is the first property. Second property, in a pan-diagonal 4x4 magic square, the sum of an entry with another which is 2 squares away from it along a diagonal is always half the magic sum. Then there is a third property. In a 4x4 magic squares with entries 1, 2 up to 16, each element has the same set of neighbors in each of the 384 pan-diagonal versions. In particular, the element 16 has as neighbors 2, 3, 5, 9. So we will use all these properties and then actually generate a pan-diagonal magic square of 4x4 using numbers 1 to 16 for a sum n equal to 34. So we first use property 3. So we take a number 16 and it says these 4 numbers are always adjacent to it. So we can fill in all these numbers. So we have got already 5 numbers now using property 3. Then we will use property 2. It says in a pan-diagonal magic square, sum of an entry with another which is 2 diagonals away. So this is 2 diagonals away from here. So it must be half of 34 which is equal to 17. So we have got 1 also, right? Now we will use property 1. What does it say? In a pan-diagonal magic square, the entries of any 2 by 2 subsquare will be, consecutive rows and columns will be exactly the magic sum. Now we can actually get this number, because these 4 must add up to 34. So 16 plus 3, 19 plus 5, 24. So therefore this must be 10 to make it 34. Similarly, we can take these 4. 16 plus 3, 19 plus 2 is 21. So this number must be 31. We can take these 4 now. 16 plus 5 is 21 plus 9 is 30. So this number must be 4. And we can take these 4 now. 16 plus 2, 18 plus 9 is 27. So this number must be 7. So we have used property 1 and got all these numbers now. Then we again use property 2. What we say is this and 2 diagonals away from this will add up to half of 34 which is 17. So this number must be 8, right? Similarly, this and 2 diagonals away from this must add up to half the number. So already 2 is there. So this number must be 15 now, right? Similarly, so you have got 15 and 8 now. So how did you get this 14? This is 2 diagonals away from here. So 3 plus 14 is 17. How did you get this 12? This is 2 diagonals away from 5. So this is 12. It should be added to the half the sum. So we have got all the numbers marked here. Now we get the final. So now we can use property 1. These 4 must add up to 34. So we will get this number. These 4 must add up to 34. That is how we will get this number. So this is how the pan-diagonal magic square is generated. So what you see here is another interesting application of Indian mathematician Narayana Pandita, which with all these algorithms one can generate pan-diagonal magic squares, which is very fascinating. Now so far we have seen so many things. We started with the contribution of uniqueness of Indian mathematics. Then we saw a very large table of the contribution of Indians in various areas quickly, although we did not look any of them in detail. Then we looked at a few ideas in algebra, a few ideas in geometry, quickly touched upon trigonometry, binary mathematics, and finally on pan-diagonal magic squares. Now this must give us enough indication that Indians were not sitting ducks. They were not waiting for the Western world to tell us what is Pascal triangle and so on. It appears that much before all these, or maybe concurrently, whichever way we want to say it, I think there is a lot of work, there is a lot of development that has happened. 3 issues in conclusion I want to say. The mathematical activity is continuous, it's going on and on and on. It was not sporadic events here and there, so the society is very involved, it looks like. Secondly, it's sprinkled all over the country. Bengal, Varanasi, Kashmir, Karnataka, Gujarat, whatnot, all over the place. So this is rampant, this thinking is rampant everywhere. That is the second interesting point. And the third interesting point is they have continuously improvised, worked on the earlier one, give better commentaries, refined some of them, provided a better proof. So this is a very rich mathematical tradition. It is time that we seriously dip into it. Every Indian university must have good number of electives based out of Indian mathematics. That way we will be able to draw some of the unique methodologies that they have used and see their application, and even taking it to further dimensions of applications and theory building. I think that's what my take is when we look at this entire body of knowledge in a very limited sense through this set of videos in this module called Indians' Contribution to the Field of Mathematics.